session with David Skinner talking about Ambitwistor strings on AdS3 times S3.
Okay, well, thank you very much, first of all, to the organizers for inviting me to talk at this conference. The work I'm going to talk about is based on a paper which came out in July, which I wrote together with Kai Röhrig, and we're continuing to think about this also with Grisha. And I'd also point out that on the same day, there was a very, very nice paper by Lorenz, Schotter, and Sebastian, which covers much of the same material from a very similar but slightly different perspective. So I'd also recommend you take a look at that. There we go. Okay, so the goal is a sort of long-standing interest of mine, which is to do in ADS what we already know how to do in flat space, namely to obtain simple, compact expressions for amplitudes in the supergravity limit, but where there are n particles taking part, right? So we've got as many particles as you wish, and we want to find a nice form for this expression. Now, of course, as we've already heard in various talks, in Fernando's talk, in Georgios's talk, we definitely don't want to do this using Witten diagrams or Feynman diagrams, but instead we're going to take inspiration from the flat space limit where such expressions for n particle amplitudes already exist. And in flat space, we're in the luxurious situation that actually we have several different representations of n particle amplitudes. And the one that I'm going to take inspiration from today, the one we're going to follow closest, is one that was originally found by Kachazo, Hay, and Yuan, which states that the n particle supergravity amplitude at tree level can be written in terms of a pair of Pfaffians, which depend on the external momenta k, some polarization of the external particle, the external gravitons epsilon, and also some auxiliary points on a Riemann sphere, z. So we've got two of these Pfaffians. They're just perfectly finite dimensional Pfaffians of finite size matrices, together with the determinants coming from solving some scattering equations. So these z's, these points on a Riemann sphere, are determined in terms of some, they're determined to be roots of these scattering equations, where the scattering equations of the external momenta divided by the differences of the worldsheet coordinates has to vanish. Okay. And as I said at the top of the slide, we're not quite going to get to quite such an explicit formula today, although we're going to get pretty close. But what I hope to show you is that in getting as close as we can, we're going to make an interesting contact to integrability in a way that's different from the usual relation of integrability to expansion in the coupling constant, and instead is more to do with multiplicity. So to do that, I'm going to have to talk a little bit about Ambitwistor strings. So let me explain what these are, and we'll start in the basic case, which is just flat space. So in flat space, the Ambitwistor string is very simple. We've just got a sort of first order kinetic term for p and x, together with the constraint that p squared is 0. It's important to notice that this model is purely chiral. So the kinetic term here involves the d bar operator on the worldsheet, not the d operator. And all these fields have worldsheet conformal weights such that each term in the action makes sense. So P has worldsheet conformal weight 1, so that this thing can be integrated over the worldsheet. And that then implies that E transforms on the worldsheet like a Beltrami differential. So you can either view this as a sort of chiral worldsheet theory, or if you like, you can view it as a complexification of a world line action. Now, why do we call this Ambitwistor strings? Well, we're constraining this E acts as a Lagrange multiplier to constrain P squared to vanish. And this constraint generates associated gauge transformations, which translates x in the direction of p. So p is canonically conjugate to x, so x gets translated in the direction of p without p itself being changed. And so we identify x with any light ray through x in the direction of a particular p. And so the target space, accounting for this constraint and associated redundancy, isn't so much the phase space of our manifold or the cotangent bundle to our manifold, but rather it's the space of null rays. I should say rays. And another name for the space of null rays is just Ambitwistor space. Now, the vertex operators in this theory, if we scatter some plane waves, then they're BRST invariant. We have a BRST operator because we're gauging the constraint p squared. And these vertex operators are BRST closed precisely when they correspond to massless particles. Furthermore, unlike normal string theory, there are no in the spectrum. So normally in string theory, you get a Reggie tower because e to the I k dot x can have some anomalous conformal weight depending on k squared, depending on the mass of the particle. And you balance that with some sort of polarization operator out the front. But here, because we had a first order action, the XXOP itself is regular, it's trivial. And so this thing never has any interesting conformal weight. It's always a scalar. Okay, so if we insert n vertex operators of this type, then when we integrate out the worldsheet field, the zero mode will tell us that momentum is conserved, and the non-zero modes constrain the field P to be holomorphic everywhere on the Riemann sphere, except at the location of the insertion points, and the residues are just given by the external momentum, all very simple. So since this is what P is constrained to be, P squared, it follows immediately, just looks like this. And how does that correspond to the fact that we were supposed to be gauging P squared? We said P squared was supposed to be equivalent to 0. Well, if we handle the gauge fixing carefully, then we find that this gauge field E has got some moduli, which are just Beltrami differentials. And so that this, this term, the coupling of P squared to the gauge field in the action, we can just expand it in terms of the moduli. The Beltrami differentials extract the residue of P squared at any n-3 of the mark points. And just looking at this formula, it's easy to see that these residues are exactly the scattering equations, or those quantities I called SI. Okay, so integrating over the moduli EI then imposes that this quantity in brackets should vanish, and that's exactly the scattering equations. Was there a question?
No.
Okay. Now, depending on what theory you want to describe, you can embellish this sort of basic model in various ways. And if you want to describe supergravity in flat space, then the right way to do it is to include two sets of worldsheet fermions. So again, this is very similar to the RNS string, but again, notice that both of these worldsheet fermions are left moving. They both involve the d bar operator as their kinetic term. And along with p squared, which come from p dot psi and p dot psi tilde, and we gauge both of these as well. And of course, if you were to think that P was sort of secretly dx, then this would be very similar to the worldsheet superconformal algebra that you have in the RNS string. But P is not dx, P is an independent field. And so actually what these fields G, or what these currents G, G tilde, and H generate is a worldsheet current algebra, which is SL1/1, whose relations look like this. In particular, it's got nothing to do with the worldsheet stress tensor. So after a GSO projection in this model, you find that the complete spectrum is type 2 supergravity, A or B, depending on the chiralities of the spin fields. And the Pfaffians in the CHY formula that I showed you on the first slide come from just calculating the correlation functions of psi and psi tilde. So this model in flat space, this Ambitwistor string, in some ways it was engineered to reproduce this CHY formula for supergravity amplitudes. However, the fact that we have a model which reproduces these amplitudes tells us something more, because we know that this model gives us all the right supergravity tree amplitudes with no alpha prime corrections. That tells us that the consistency conditions for this model on a curved spacetime will just be the Einstein equations. Because if there are ever any higher order corrections, higher derivative or higher powers of curvature corrections in the consistency conditions, they would have showed up as in some n particle amplitude at tree level for sufficiently many particles, and they didn't. So that's true, and we're going to look at it today in the specific case of AdS3 cross S3. So there are two reasons for specializing to AdS3 cross S3, both of which are just to do with simplicity. Firstly, of course, it's a group manifold rather than a coset. But of course, much more fundamentally, it's a solution to the Einstein equations if we just include another Schwarz flux. So to describe supergravity on higher dimensional ADSs, as well as using a coset, I'd also expect to have to include Raman flux in the background, and that will require a pure spinor version of this Ambitwistor string. So there's been some work at the classical level done on that already by Chandier and Valillo, but I'm not going to talk about it today. So we're going to stick to this basic case. Okay, so the action in this basic case looks like this. So we've got a field J, which is the curved space equivalent to P. And again, J is not related to the field G, which describes the map into the group manifold. Okay, so in particular, J is not G inverse DG, as it will be in a normal WZW model. It's just an independent field. And again, we're going to couple, because we want supergravity, we're going to couple to two pairs of fermions, which I'm calling psi and psi tilde. And it's convenient, although not necessary, to take one of these fermions to be covariant and one of them to be invariant, or right invariant at least, under translations of G on the group. And at the same time, just as we gauged p squared and two fermionic currents in the flat space model, we're going to gauge a bosonic and two fermionic currents, a bosonic current H and two fermionic currents G and G tilde. Let me also remark that in writing the kinetic terms for these fermions, I've chosen some metric on the group, this M, and this metric should be bi-invariant, but we'll see that actually it can't be the killing form. In fact, we require that the trace of the killing form with respect to this metric vanishes. Okay? So that would be a problem on a simple group, but on a non-simple group, we're fine. Non-semi-simple group, we're fine. Okay, so what are these currents? So again, they're pretty much straightforward generalizations of the flat space case. Instead of p squared, the bosonic current now just becomes j squared, where again, the indices are tied together with this metric. And the two fermionic currents involve j dot psi tilde, together with some term involving the structure constants, involving the commutators here. And you can check that you can compute OPEs in this model. You can check that these currents obey exactly the same algebra that we saw before in flat space. Potentially, there are some higher order poles in the current algebra, which correspond to anomalies in the algebra, but they vanish precisely when the M trace of the killing form is 0. And you can also check that this condition is precisely what's left of the Einstein equations. This is what you require in order for this background with metric M to satisfy the Einstein equations on this AdS3 cross S3 background with NS flex. Okay, so exactly as we expect. So again, there's an associated BRST operator. It gauges these three currents as expected with ghosts C tilde and then two bosonic ghosts gamma and gamma tilde. And we also gauge the stress tensor separately. Okay? And I remind you one more time that the stress tensor is not j squared. The stress tensor is j into g inverse tg, together with some fermion terms. And you can check that provided this condition on M holds and that we're in 10 dimensions, that this BRST operator is anomaly free. So I've said that we should really be in 10 dimensions. That's the only condition here that comes from the stress tensor. In particular, there are no sort of field equation conditions coming from the stress tensor. And really that means that to have a fully anomaly-free model, we should be on AdS3 cross S3 cross some compact 4 manifold, which we'll take to be Ricci flat, but I'm just going to ignore that 4 manifold for today, as usual. And just as we found in flat space, you can check that the spectrum of this BRST operator precisely corresponds to type 2 supergravity on AdS3 cross S3, linearized around that background. And the basic vertex operators look like this. They've got some ghost factors, a pair of fermions, and then some function of the field G, a map field. But unlike in normal string theory, precisely because there's because the OPE between G and G is trivial, there's no normal ordering issue in this V. Okay? There are some conditions that the function VAB of G has to satisfy if it's to be BRST closed, and they indeed correspond to the linearized Einstein equations. But it's very simple to write down the vertex operators precisely because the OPEs are much simpler than in a full string theory. Now, in the particular case we're going to be interested in, of course, we're going to look at bulk to boundary propagators. And for gravitons, the two polarization states of the gravitons corresponding to the holomorphic and anti-holomorphic stress tensors on the boundary, you can write bulk to boundary propagators for those like these. So in the numerator, there's some sort of polarization data. In the denominator, there's the sort of usual bulk to boundary propagator factor. And here, my notation, so we should think of G as now living just in the AdS3 part, so just in the SL2 part. And so it's a 2x2 matrix. And I can track that 2x2 matrix with a 2x2 matrix of determinant 0 corresponding to a boundary point on the boundary. So borrowing spin helicity notation from 4 dimensions, I might write it in terms of a pair of spin. Or I might just write it in terms of a local coordinate x and its complex conjugate x bar on the boundary. Okay. Now, the worldsheet correlation function, which is what in flat space gave us the Pfaffians in the CHY formula, in particular when we integrated out the psi's. Again, here, you can compute it exactly using the JJ and JPsi OPs. You can do that even at n points. So for arbitrary multiplicity, the expression is a little bit complicated, so I won't give it right now, but it's in the paper. And typically what you find is that for simple choices, in particular, if you scatter scalars, you just end up with a D function that's coming out of the worldsheet correlation function. Whereas for more general scattering of either gauge states or gravitons, you end up with some differential operators corresponding to the polarization vectors acting on the D function. But it can all be explicitly written down. There's no worldsheet path integral left to do. Of course, the meat of what we're studying is really from understanding what the scattering equations are going to be on this AdS background. So just as in flat space, they're going to come from understanding the moduli of this constraint that h was 0, and h, of course, is a half j squared. And j at the moment is an operator in the CFT, but if you study its OP with the vertex operator, you can check that this particular combination, j squared, acts on the bulk to boundary propagators in this way here. Okay, so there's some potential double pole terms, which comes when both j's act on an individual vertex operator. But these double pole terms vanish because the numerator here is just 0 for our case. Again, that just follows from the representations of the states that you're trying to scatter on the boundary, or alternatively, you can just say it's just the massless condition in the bulk. It's just the fact that we're scattering massless particles. But there are also simple pole terms, and they take this form. Okay, so there's a simple pole when Z goes to any of the worldsheet insertion points, and its residue is this thing that I'm calling HI here. And these operators they generate SL2. There's the standard raising and lowering and spin Z operators for SL2, but acting on the boundary points here, the boundary point of the ith particle. And of course, in this audience, everyone will recognize that this is exactly the Hamiltonian. Acting on the boundary coordinates. So from a spin chain point of view, what's happened is that the worldsheet insertion points here have become the inhomogeneity parameters, the particular values of the spectral parameters associated to the spins, where these spins are determined by the quantum numbers of the dual boundary operators. And in particular, they're always in representations such that there's no double pole. The quadratic Casimir vanishes. Now, of course, this go-down Hamiltonian is not too far removed from standard WZW models. Normally, if you look at the Konishnik-Zamolodchikov connection, you find that the worldsheet correlation function, this psi, which depends on some boundary points perhaps, and also some worldsheet points, is a flat section as you move around, a flat section with respect to the Konishnik-Zamolodchikov connection as you move around in the moduli space. And of course, this has come because you've inserted it's a Ward identity for the worldsheet stress tensor. And that's why, on the one hand, it's related to worldsheet translations, and on the other hand, writing it in its Sugawara form, you get it in terms of this go-down Hamiltonian. Here, j squared was not related to the worldsheet stress tensor, so we don't expect to have this worldsheet derivative term. And instead, what we're supposed to do is we evolve our worldsheet correlation function through the go-down times. Okay, so we want to evolve it using the go-down Hamiltonian. And of course, the way to do that really is to expand it in a basis of eigenfunctions of the go-down Hamiltonian. That's what I'm calling these states E here. And then this Hamiltonian, we replace it by its Eigen States, and we can do the integral over the E. They're just Beltrami differentials, so they just pick out residues of the eigenvalue of H, and I'll call those residues, I'll call them EI. Okay, and once again, in the quantum field theory, in the worldsheet theory, we're supposed to integrate over the moduli, these EIs, and again, that'll impose the scattering equation. So when I integrate over the moduli of this field E, these things I'll interpret as delta functions, and they tell me that we should choose our marked points so that the energy eigenvalues of the go-down Hamiltonians all simultaneously vanish. It's a sidetrack, but I can't resist mentioning that there's an analogous relation here to I mean, you can sort of you can find the same sort of thing from the Konishnik-Zamolodchikov equation in a standard WTW model if you take the limit where the level goes to this critical level, which is minus the Joule-Coxeter number, so that this term blows up in comparison to that. And then this just becomes a constraint that this thing is annihilated by this Godin Hamiltonian. Taking this level, the critical level, is somewhat analogous in AdS to what in flat space would be the Gross-Mendel limit. You see, you're sort of saying that the energies are strong and are very large in string units. That's the Gross-Mendel limit in flat space. And it's long been noticed that the scattering equations in flat space also play a role in the Gross-Mendel limit. And I've always thought that was really just a coincidence. And I think I probably still think it's just a coincidence, but certainly very striking that the same coincidence appears again in AdS. Okay, so that was kind of abstract. I said there exist these eigenstates and there exist these eigenvalues. Can we say something a bit more specific about what they actually are? Well, the operator H, that was a quadratic differential on the world sheet, and it had simple poles at all the mark points. Right, that was this thing here. We didn't have these double poles. We had simple poles at the mark points, and the coefficient was an operator. So furthermore, the residue at any simple pole itself was a one form on the world sheet, which had simple poles at all the other mark points. So the eigenvalues of H and of its residues must take the same form. So we just write down the most general form of that. Instead of being operator valued sections of these things, they'll just be straightforward sections of these things. So the eigenvalue of H itself will take the form of this with some parameters tau ij, and its residues then, which I'll call ei of z, just take this form. Now, we said that our operator hz had no double poles. That was really just the master's condition, and that corresponds to the fact that, so we have to constrain these parameters tau ij so that the diagonal term tau ii vanishes. And again, that's just the statement that we're scattering massless particles on AdS. But similarly, there were no poles at infinity. Okay, we had a well-defined world sheet theory, and there was nothing interesting happening at infinity on the world sheet. And so there was no pole at infinity in Z in H, and that's because the operator J squared didn't have any singularities at Z equals infinity because there was no insertion there. And to ensure that that's true of these eigenvalues as well, we also have to constrain the sum over J of tau ij to be 0. And really that just amounts to saying that our world sheet correlation function satisfies a Ward identity for global SL2 transformations actually on the boundary target space. Okay? So these two conditions are very much analogous to what you get in flat space, where this would come from momentum conservation, and this would come from the fact that you're talking about massless particles in flat space. So the AdS scattering equations are again going to be that you should choose the Zs, you should choose the insertion points so that these combinations vanish. And that's exactly the same form as the scattering equations you had in flat space, except that in flat space where the numerator would have been Mandelstam parameters, here there are these parameters tau ij that we haven't determined yet, other than by these relations. Okay? And I'll just mention that these tau ij's are certainly related to Mellin parameters, but they're not actually equal to the Mellin parameters. Now, that's what we can say about the eigenvalues. What about the eigenstates themselves? What sort of eigenstates should we consider? And well, they're eigenstates of a Godin Hamiltonian, but they have some special properties. Firstly, because our world sheet correlation function is invariant or perhaps covariant under global SL2 transformations of the boundary, and because our Godin Hamiltonian commutes with the global SL2 generator, so it won't mix. There won't be any overlap between states of any different SL2 global transformation properties than psi. Okay, so in particular, we need states that are also invariant under global transformations of the boundary SL2. And furthermore, we have this unusual requirement, unusual from the point of view of spin chains, that our states are invariant under a world sheet SL2. Normally, you wouldn't take the spectral parameter in the Godin model to live on a Riemann sphere. You'd just take it to live on the complex plane. But it's really important to us what's happening at infinity. So
you have a few minutes left, David.
Thank you. So the beta states here are not enough. In particular, the beta vacuum breaks the global SL2 transformations on the boundary. And so instead, we should use separation of variables. And this is what I'm currently looking at with Kai Röhrig and with Grisha. But as we already heard from Fedor, to get to the separation of variables representation, what we should do is look for the zeros of an operator that Fedor called B. Here I'm calling it F. It's just the lowering operator of the whole system. And we diagonalize this operator, since it corresponds to translations of the boundary, we diagonalize it by taking a Fourier transform. Of course, that's a little bit delicate, and this is what we're trying to understand at the moment, because this Fourier transform doesn't really sit very well with global SL2 transformations of the boundary, because it's in danger of introducing an essential singularity at infinity when you take the Fourier transform. There is, however, a simplification. Because we're going to, once we integrate over the moduli, we're going to impose these scattering equations. When we then integrate over the worldsheet insertion points, as you would do in any string theory, these worldsheet integrals are localized by the delta functions that impose the scattering equations. And so Z has to sit at one of the solutions to these scattering equations. Okay, so we get some Jacobian from solving these scattering equations. But then in the rest of the correlation function, we only need to know its value when Z solves the scattering equations. In particular, we only need to know these eigenfunctions of the Godin Hamiltonian at these very specific values of the inhomogeneity parameters. Okay. And to see how that simplifies, let's look at the case of n equals 4. So in general, you can check that the Godin problem for the 4-particle state boils down to this second order ODE, which depends, of course, on the energy eigenvalue. And the general, and here it's written in terms of the cross ratio both on the boundary and on the worldsheet. Now, the general solution to this equation is a little bit complicated. It involves something known as Hoyne functions. However, when you choose Z so that the energy vanishes, then it simplifies, and the solution you can write down straightforwardly. It's just up to an overall factor. It's just a constant or some term depending on logarithms. So we expect that these eigenvalues in the general case are going to simplify quite dramatically on the support of the scattering equations, which is all we need for the amplitude formula. Okay, so let me just conclude. So what I've hoped to convince you of is that there really do exist compact expressions for scattering amplitudes on AdS in supergravity for arbitrary numbers of particles. I'll also point out that there are very similar scattering equation type formulae for Yang-Mills theory or for the biojoint scalar. And in AdS, the scattering equations themselves really take a form that's remarkably similar to that in flat space. They take exactly the same functional form, except that instead of Mandelstam parameters, we have these parameters labeling the eigenvalues of the Godin Hamiltonian. I only spoke about states that were invariant under the S3 part here, although the S3 was crucial for the consistency of the model. We only considered states that were zero modes of the S3. To include the S3, of course, we just extend our Godin Hamiltonian to include an SU2 factor, and those states, the additional complications can be handled by just the beta ansatz in the SU2, because we just got compact representations. That's fine. The amplitude formula itself looks like this, where psi is the worldsheet correlation function, which I've claimed we can explicitly figure out, but I didn't show you exactly what it was, and where these E's are the Godin Eigen States. And all I want to point out is that the form of this is somewhat reminiscent of scattering wave packets in flat space. So the natural thing to scatter from this point of view is the individual Godin Eigen States, but somehow, because what we decided we were going to scatter was of course, local bulk to boundary operators, that's like taking a wave packet of these individual scattering eigenstates. And finally, let me say that the formula where instead of the supergravity amplitude, we consider a biojoint scalar amplitude here, which again is very easy to write down. This thing is just some part Taylor factors times a D function. That formula has been proved in this other paper I mentioned by Sebastian, Schotter, and Lorenz, proved by taking this formula and unpacking it back in terms of Witten diagrams, comparing it back in terms of Witten diagrams. Okay, so thank you very much.
Okay, thanks very much, David. So we have a few minutes for questions.
I would like to ask a question.
Go ahead, Pedro.
Hi, David. Are these these wave packets that you consider with separation of variables, do they have a counterpart in flat space? If I take the flat space limit, do they go to the usual plane waves, or would they go to a new set of wave packets in flat space? And the other, okay, that's one question, and I have another one.
Well, the first question, so in flat, the normal plane waves already diagonalize. So instead of the go-down Hamiltonian, you'd sort of have an abelian go-down Hamiltonian, right? Instead of the SL2 generators in the numerator, you'd have just translation generators. And you diagonalize those by plane waves. That's what going to momentum space is. So yeah, so just the process of going to momentum space in flat space and saying that you are indeed going to scatter momentum eigenstates as opposed to some other solution to the field equations, that already diagonalizes what you might think of as the flat space go-down Hamiltonian. And now whether if I take the flat space limit of AdS, these eigenfunctions reduce to that, I'm not sure, because I don't explicitly. I mean, you know, I said we wouldn't quite get to the end of this goal because I don't have a completely explicit formula for these eigenfunctions. So I don't know. They do have interesting limits. Yeah, they do look kind of interesting when you take the limit that the world sheet degenerates in terms of Mellin parameters. They do look quite interesting. So I suspect the answer is yes, but I haven't checked that.
My other question was, how could you make contact with AdS Grossmende? Because AdS Grossmende should be about a big string that involves all massive string states, and you only see supergravity. So I really did not miss that comment. How could you ever make contact with an analog of Grossmende for AdS? That should be about a big classical string, no?
Yeah, I mean, again, I'm being a little bit heuristic here. All I'm pointing out is that in what you might call the Grossmende limit, which is when you go to this critical value, the world sheet correlation function in a WZW model is constrained to be an eigenstate with energy 0 of the go-down Hamiltonian in the same way as we have here. But
aren't you now that you are doing a low energy expansion, so you cannot go there, right?
No, I absolutely agree. And you know, I mean, all I'm saying is that the same equations crop up. You could ask me in flat space, isn't it mysterious that in the infinite tension limit, the supergravity limit of the string theory, you have these scattering equations, which are the same equations you have in the tensionless limit of the Grossmende limit? And yes, it's mysterious, and I don't really know what to make of it. Let me perhaps point out one other curious feature. So this is the equation that determines our eigenfunctions in the n=4 case. And I said that the general solution was one of these weird Hoyne function things. You should think of these things as a sort of generalization of hypergeometric functions, right? You can see that this differential equation has got singularities when the cross ratio is 0, 1, also infinity, but also at this extra point when the world sheet cross ratio and the boundary cross ratio coincide. Now, that point is interesting in other work by Eberhard and Gaberdiel and Gopakumar, where they study exactly the tensionless limit of the full string on AdS3 cross S3. They certainly seem to find that, you know, they get interesting behavior. The solution seems to localize on maps where exactly they have a covering map. In particular, the world sheet holomorphically covers the boundary cross ratios. So yeah, I don't know. I don't know that there's anything deep there any more than I know there's anything deep there in the flat space case, but there are certainly some intriguing connections.
Okay, so let's postpone further discussion for the discussion section. So now we can go to the second speaker today, which is Bogdan Stefanski, who will talk about Chern-Simons origin of superstring integrability.
So let me try to share my screen. Let's see if I can get this to work. So can you see this?